So the word kinetic, what does it mean for you guys? Kinetic, where have you heard it? So kinetic has to do with movement, right? Kinetic energy has to do with energy associated with movement. So kinetic energy is energy something has because it's moving. The faster it moves, more the kinetic energy it has. That's it, nothing else. As the definition, energy which a body possesses possesses by virtue with respect to of being in motion. So we have two small derivation. You guys are used to all of this, but let me do it off. So we are looking at expression for kinetic energy the classical way. The first one is what? Using equation of motion, and then we'll use calculus. So we have expression for kinetic energy. Okay, so that's what we're looking at. Case using equation of motion. Equations of motion. Okay, so we need a diagram wherein we have an object and it has a mass of m and it moves. It's made to move. It has a force of F and it gets displaced from point A to point B, and the displacement here is S. Time t is equal to 0 second, and this is t second. And we can consider up and right as positive. And we'll consider this to be frictionless. So basically this slides. Okay, so let's start off. So we know that v square is equal to u square plus 2as. So from here, if I consider, which I have actually, I have not, u is equal to 0. If something starts with 0, then v square is equal to 2as, or I want expression for a. Actually, a is equal to v square by 2s. Now, where is that I am going with this? Well, we know that work and energy are related, right? So, I'm moving on to, we know that work is equal to force into displacement. So, we have Fs cos theta. That's where I'm going to. Now, our force and displacement, they are in the same direction. So we have theta is equal to 0. Reason, force and displacement are in, sorry, you guys won't be able to see that, are in same direction. Then what else do we need? And that's it. So, and F is equal to m into a. That also we can substitute, and also F value eventually. So a value eventually. F or m into a instead of F, m into a, cos of 0. This is equal to 1, and a is v square, what is it guys, by 2s. Okay, I forgot s itself, my bad. This is force into displacement. Okay, it doesn't matter, you guys can understand this, right? And there's still displacement over here, s. So what happens? S and s gets cancelled, and so we have work is equal to the famous kinetic energy expression, half mv square. So we'll write a small statement. The work appears as kinetic energy, and therefore kinetic energy has the expression half mv square. Okay guys, there is a small variation. If the object had an initial velocity of u, we have kinetic energy is equal to half mv square minus half m u square, right? Because this is the work done, this is the contribution. If the initial velocity was 0, but if it already has some initial velocity, then the new velocity is a combination of what already it had minus, we need to extract that off. This is the amount of work done. This is the exact amount of work done, So if there was some initial velocity, this would be the condition. It's like I already had some amount, someone else gave, and my account is now 100 rupees. I had 10 rupees. So how much did the person give? I have 100 rupees in my account as of today. I had 10 rupees yesterday. What is the amount that the person gave? Yes, 90 rupees. Because he gave 90 rupees, I ended up with 100. But because I already had 10, it ended up with 100. Not because the person gave me 100. You're getting the funda, right? So that is one. So next derivation is, how did I write it? Case, right? So, okay, case, what do we have? Using calculus. Okay, so why should we use calculus? When we have varying things, So let us look at it. For a small time interval, dt, let displacement be ds. So therefore the small work we do within this small duration is f ds dot product, right? We'll consider for force and displacement to be in same direction. We have theta is equal to 0 degree. Therefore, dw is equal to ma ds cos 0, right? Then we have m dv by dt ds. Then if I rearrange this, I'll get velocity. How do I get velocity? I'll just write this, and this expression is nothing but your velocity. Okay, now the total work, when we have this is your small work, right? This is your small work. So this is your small work. The total work, how do you find out total work? Integration, that's it. When we have done the work from work 0 to w by changing the velocity from vi to vf, so mv dv, right? I applied some force onto some object, the velocity changed from say 0 to v, then this will be mv dv will be mv square by 2 0 to v. Okay, and we have work is equal to half mv square. Again same thing, this work, if it appears as, it changes as the work, if it appears as movement, then we have kinetic energy is equal to half mv square. Obviously, there is change in velocity is what we are trying to show. Okay, so let me come back. So we are looking at kinetic energy. Kinetic energy is the energy that an object has because of its motion. Now we are trying to, or I already showed the derivation for kinetic energy. See, that is, if I have an object, if it was stationary or if it was already moving, it doesn't matter. And I change its velocity, then the work that I have done has transformed into some form of kinetic energy. Actually, not some form of kinetic energy, it's transferred to kinetic energy, right? So this is an ideal scenario wherein I have an object of m at time t is equal to 0, the velocity was 0, I applied a force of F. For a time interval of t, it got displaced by s, and so on and so forth. So if it's just a normal scenario like this, we can directly go with Fs cos theta, and F being your mass times of acceleration, and acceleration having this expression. On substituting, we'll get a simple straightforward answer, half mv square. But if we are varying things around like this, even then we'll be able to get the same result, right? Same result, even for varying scenarios. Again, as usual, you'll understand better with set of examples and numericals basically. So yeah, for now, please copy this. Derivations are a step towards numericals. So you'll understand any derivation better when you apply it, right? So we'll derive the same thing again with numbers. Then it'll make a lot more sense. So for now, it's an introduction, just copy it. And you have to copy this as well.